Hello friends, my name is David, and recently the James Webb Space Telescope has detected a star made of a type of matter that we cannot directly see. We can only observe the effects of its presence and from that, predict that it exists in the universe. I am talking about a dark matter star. As you may already know, dark matter is a special kind of matter that neither absorbs light nor reflects it. So, has the mystery of dark matter, which has puzzled scientists for nearly 90 years, finally been solved? And is it possible that this very dark matter gave birth to stars and black holes in the universe? Dark matter has always been one of the greatest mysteries in physics, one that scientists have not yet been able to solve. To understand the connection between dark matter stars and normal stars, we need to go back in time to the very moment when the Big Bang occurred and the universe began. Immediately after the Big Bang, positively charged hydrogen atoms started forming in the universe. But at the same time, the universe was expanding rapidly and cooling down. Because of this, just 20 minutes after the Big Bang, there came a turning point. The expansion had caused the universe's total energy to drop so low that hydrogen fusion stopped completely. Now think about it. If hydrogen atoms never fused, what would have happened? Without hydrogen fusion, stars could never have formed. As we know, stars are created only when hydrogen atoms fuse to form helium atoms. That means, in the early universe, stars should never have been created. But clearly, that is not the case. Stars exist even today. So, how did this happen? What triggered star formation? Here, scientists faced a mathematical gap. The results were inconsistent. So they had to predict the presence of a special type of matter, which when added to early universe conditions, allowed hydrogen atoms to fuse. This special matter came to be called dark matter. As I said, when you add dark matter into the Big Bang theory, suddenly the calculations start making sense. It's like finding the missing puzzle pieces that make the whole picture complete. And the effects of dark matter's presence have been experienced many times in scientific literature. For context, dark matter does not interact with any particles except through one force, gravity. So for now, just remember this: gravity is dark matter's best friend, and their bond is strong.
To test this, the researchers used a supercomputer to recreate early universe conditions. They found that dark matter particles, WIMPs, first formed a donut-shaped disk. As this disk evolved, it collapsed into a supermassive black hole in only 270 million years. In a way, this study supported the theory of dark matter stars. And as you all know, in science, evidence is most important. If dark matter particles could create black holes, then why couldn't they create stars too? Building on this, astrophysicist Catherine Fries and her team created a theoretical model for the formation of dark matter stars. According to this model, these stars contain both dark matter and normal matter, hydrogen and helium. To explain in simpler words, normal stars form from cold hydrogen clouds, known as nebulae. Inside a nebula, gravity pulls gas molecules inward, while pressure pushes them outward. Eventually, gravity wins. Gas accumulates at the center, density increases, and the temperature rises. A protostar is born, which becomes hotter and denser over hundreds of thousands of years. Once the core reaches about 15 million degrees, hydrogen begins fusing into helium. and a star is born. In dark matter star formation, the process is similar except for one difference. Instead of hydrogen molecules attracting themselves, dark matter clouds provide the gravitational pull, capturing hydrogen atoms. This is called dark matter capture. These dark matter particles then supply extra energy, which triggers fusion. The fusion releases so much energy that dark matter stars shine up to 10 billion times brighter than the sun. Unlike normal stars, nuclear fusion in dark stars begins because of dark matter. But until recently, this was only theory and simulation. Then came the first experimental evidence. Last year, the James Webb Space Telescope, during its advanced deep extragalactic survey, discovered 3 galaxies that appeared to be 13.4 to 13.6 billion years old, just 200 million years after the universe formed. This was a huge contradiction, because galaxies normally take about 1 billion years to fully form and mature. So Catherine and her team proposed that these objects observed by JWST were not galaxies at all, but dark matter stars. Since no scientist had ever observed a dark matter star before, Catherine created a test model using software called TLUSTY.
The program takes a star's properties as input and simulates its atmosphere and structure. Catherine focused on spectral data, the wavelengths of light absorbed by the star, and built a framework. When they compared this framework with JWST's observations, they faced a problem. JWST usually provides both images and spectral data, but in this case, there were only images. Still, they plotted the data against their simulated dark star model. The graphs showed strong similarities, suggesting that the objects could indeed be dark matter stars. In short, Catherine's team provided the first possible proof that dark matter stars exist in the universe. But is it really true? Catherine herself noticed some loopholes in her methods. The first problem is with reference objects. To identify something new, we compare it with something known. But here, they compared the observations with a dark star model that exists only in simulation, not in reality. Second, JWST only provided images, not full spectra. The spectral data was calculated indirectly, which causes information loss. It's like looking at a cake through a straw. You might know its color, but you cannot see the whole cake or understand what it's made of. Third, JWST has a limit to its magnifying power. If an object is smaller than its resolution, the telescope will only show it as a blurry spot. In this case, the test objects were about 10 million times smaller than JWST's resolution. That means classifying them as stars instead of galaxies may not be scientifically correct. In fact, Curtis Lake, the first astrophysicist to observe them, had initially classified them as galaxies. So, all in all, to truly conclude that these objects are dark matter stars, we need clearer images and more detailed JWST data. And by the way, JWST recently detected something else astonishing: an exoplanet almost exactly like Earth. NASA scientists were thrilled. It was massive news. So friends, if you learned something new from this video, don't forget to like and subscribe for more such interesting content. See you next time. Stay curious. Keep learning.